welcome back. Tushar here. This week we are going to look at some of the theory behind technical drawing, also called as engineering drawing or British standards of drawing. The example of the drawings I'm referring to, it's actually showed in the blurred out view there on the screen right now. And this is what a technical drawing looks like. Typically, if you're not aware of, if you're new to designing, if you're new to drawing. Just a very quick introduction. Why it's necessary to study this in engineering. As you already know, it's a very complicated affair, and generally we are working with multinational companies. We are working with international scenario where language can be a bit of a barrier, and this is when it's really handy to be able to have a generic, universally acceptable mode of communication, and that's exactly what engineering drawing allows us to do. It's basically a language we engineers can use to be able to speak to one another. If you imagine working in isolation of language barriers, that's the ideal world, really. It's also it allows lots of flexibility in terms of communication between different teams of different department, within the company, or if you're also dealing with international suppliers, partners, and that's pretty much the scenario these days, really. I mean, you will hardly come across a big company who that doesn't deal internationally, and this is when you probably want to think about the language barriers in the process. Most of the time, and just to put it bluntly, in England, we are known to be the hub of designing, but we do end up sending our designs overseas, in Far East for manufacture, and this is when the language can be a bit of an issue. But in comes the British standards of drawing, really, where if you say, well, this is the standard, everyone's going to follow that, everyone understands what that means on the piece of paper, then probably we minimize the risk of, as I previously stated on my earlier slide here, risk of wastage, risk of cost, labor, time, etc. All of that is really, really valuable, especially for budding engineers. You need to be mindful of the sustainability issues within engineering. There are a few basic types of or engineering drawing. Basically, we go with the simplest to the technical ones in that particular order. Concept drawings and design layouts are basically very flexible initial stage drawings whenever you're designing a solution to a problem, while as the manufacturing one and the assembly one are actually more specific one, and I have a few examples of all of these in that order. So concept drawings will generally be very crude, rough, sometimes hand-drawn, without the use of the instruments, just block diagrams, just to be able to convey the potential solution to a problem. It could be anything. It could be designing a small gearbox where you just want to draw the configuration of that, and so on and so forth. Or maybe you just want to specify a small concept. All of that can be done with the concept drawing or conceptual design. And the example is shown on the screen here, where we're looking at 3 different concepts of mixing concrete. And the challenge here is to design the dry mechanism. Now, the dry mechanism can be direct drive, as you can see in the middle example here, or it can be a belt-driven system, or it can be a combination of belt and some gearing mechanism there, as you can see. So there is this is what's called concept drawing. It doesn't really convey much information to the reader apart from the general arrangement or the overall concept of what the problem will solve. For example, there are no dimensions. We don't really know how big the bucket is. We don't know what the motor is. We don't really know what kind of coupling we are using, or what kind of a gearbox there is, etc. So, and as I said, this is a very crude concept drawing only. Now, this can then be refined further into something that's called design layout, where we generally start to make some decisions in terms of the material thicknesses or the materials, etc. Okay, and here is an example of what a design layout looks like. where, as you can see, we're looking at a sectional view here, where, and there's a lot more detail in terms of, how exactly is that driving going on really. We got the shaft, we have some, there's a lot more detail in terms of the gearing mechanism. We got the pulleys, all of that, and this is exactly what's known as, is called design layout. But the one which we are going to be specifically focused on, it's called manufacturing drawing, or a detailed drawing. Okay, this is what you would probably spend most of your time working on, and this is what's probably a major skill for you to pick up at your degree level, and take it for your placement, for your to your employer, or your in your working career. So in a nutshell, manufacturing drawings are manufacturing instructions on a piece of paper. So what that really means is everything a person would want to know, a company would want to know to be able to manufacture an artifact. You need to include that on the drawing paper, So, and what is that information? First of all, it's all the essential dimensions and tolerances. It's necessary. I think this is the obvious one. You gotta communicate how big things are. Okay. If there are any special machining marks, etc., if you want it, finished in a certain fashion, you need to specify that on the detailed design. If you want to use a certain type of material, that's got to be specified. Any heat treatment, any post-processing, you would need, all of that has to be included on the drawing. And if you want any scribe marks, any identification marks left on the part, etc., so all of that is included. Engraving, embossing, etc., is all of that is included on the manufacturing drawing. Here's an example what it looks like. I find it easier to look at this drawing and break this space in two halves. On the right hand side we have lots of words, and on the left hand side we have a drawing. So we tend to describe everything as much possible in the drawing format. However, when we, on the right hand side, whatever we just cannot describe in drawing format, we resort to using language. Basically, we use words, and we'll walk through them now. Okay. Before we proceed with that, it's probably worth noting the fact that this is the same object. You're looking at it in different directions. So one is probably the front view, one is the top view, or we got the front view on the bottom, whichever way you look at it. But I think the crux of the matter here is it is the same object when we are looking at a different direction, etc. And all of these dimensions kind of they tally each other. That if you were to draw projectors, it will all end up with the same drawing. So that circle there, right there, it's R25, means it's radius 25, and it also if I were to draw some thin lines here, that then projects back into this slice, which is 7mm thick. We have loads of other stuff going on here. For example, there is a 3/4 circle in there, and you may realize, what is that? That's actually a threaded shaft right there. That's what that means. So whenever you see a double line, that's an indication of threads. We don't really generally sit there and draw threads. There is a standard for that. Exactly same is happening up here. We have a smaller M6, which is not a motorway. It is M is for metric, and 6 is the nominal diameter of that thread shaft there, and it's 13mm high. So all of that information is given about that spindle right there. Also, very interesting detail right here is, if you can imagine, material is being scooped out in a spherical manner, basically. So this is a cavity underneath, and when you look at it from sideways, the cavity is actually it is concealed on the inside of the model here. Hence, we have to resort to drawing that using dashed lines, because that is concealed. And once again, that detail is conveyed around here, which says SPH, spherical, radius 9, and that tallies to that circle there, which is basically that detail around there. So as I said, you need to look at this drawing and probably try and make sense of how are those views correlated. Now, looking at the right hand side, there's tons more information on here. For example, the scale, as you would appreciate the fact that we have to specify scale 1:1, dimensions in millimeters. UOS means unless otherwise stated. So wouldn't it be funny if you were to just start writing units right next to every single one of those numbers? And to be able to avoid that, we go with this, a statement, a blanket statement that covers all the numbers on the screen, which is pretty handy, I would say. This right here is a projection symbol. And later on in this presentation, you will realize there are a couple of different types of projection symbols and a project system, and it's necessary for us to specify which one we are following. Now, this is the more popular projection system anyway, so we don't need to, we will get used to looking at this particular icon all the time, okay? Because this is a more popular system. What material would you like that to be manufactured from? So that's steel of some grade, not specified here. What kind of tolerances we're looking for. So tolerances generally means whenever we have a number like this here, what that really means is we are okay with 11.9 or 12.1. So if the manufactured piece doesn't really have that as a .12 millimeter dimension, it will still work as long as that's within the tolerance. So that's basically the forgiveness limit. As long as that's within the tolerance of that plus minus 0.1 of a mil, and that will still work. That's what tolerancing means. Clearly, it's a big science, something we should be very enthusiastic about in terms of knowing a lot more about it, because this is all to do with how to be a better engineer, how to be a better designer. What kind of finish you would like to see on the part after you finish. So after it's finished, any details you would like, or you like it painted or whatever, sandblasted, let's just say, that would go in that space there on special instructions, as in remove all the burrs and sharpages. So just deburr the whole of it. Company logo, the author, date created, and more of that stuff. So this space right here, it's called the title block. Okay, and these are your drawing views, which gives you all the information about the manufacturing of that particular model. Now looking at the assembly drawings, which is probably a slightly higher level, however not as complicated as the detailed drawing. We use assembly to be able to communicate the way things are put together in a multi-body or in a multiple part mechanism. Here's an example. So here we are looking at probably 3 to 4 parts. Yeah, 4 parts around here. So we have this this big chunk of metal, basically the bracket, that's basically a chassis for all the parts to be assembled on. So we have the bracket here. Following that, we have a big pulley. So that shape around there, which is also very clear from this view here, is the pulley. Following that, there is a pin that goes in to keep it all together, probably threaded in, and there is also another pin that's seen that in that particular view there, that's also in there. Okay, so this is just an example of what an assembly drawing looks like, and as you may appreciate the fact that there aren't very many details on this, and this is exactly how it's meant to be. This is not a detailed drawing. This is an assembly drawing. So generally, you are expected to supply an assembly drawing as an overarching document, and then you also provide the reader with detailed drawing. So the pulley will be drawn separately with all the dimensions on there, and the bracket and the pins, etc. So they would all have their own individual detailed drawing. However, assembly drawing is more about the overall dimensions, how big things are once they are put together, or what is the procedure for assembly. And this particular technique is called ballooning, where we literally click, drag and drop, and we get a number, and then we cross match that number with a bit of a description and the number of repeats. You may have more than one pulley or one part in the same assembly, and so we generally use that space to be able to say how many we need, also known as bill of materials. Really important term. Just remember the fact that in assembly drawing we will never include detailed dimensions. It's all to do with overall dimensions. Now, looking at the basic needs and the fundamental types of drawings, it is pretty clear that we all of us need to know a standard of drawing, which is known as the BS, British Standards 8888. Okay. So, what does this standard say? It makes a recommendation in a variety of forms. Number one, the title block. The title block should contain all of this information, which is fairly straightforward, easy to understand. I don't think this is particularly difficult. A name probably of the author, date when it was created, projection symbol, original scale, title, drawing number, etc. And obviously it's a standard, and this is a legacy problem that we generally have larger margins on the left hand side and smaller on everywhere else to be able to allow for binding. But that has become a standard now, and we generally tend to follow that. Most of the times the drawings are not, they don't end up in a file anymore, they are on a computer. However, it has still become a norm to keep it that particular way. And as you can see, the title block goes round at the bottom right hand side corner, and rest of the space is your drawing area. This is where you can organize the views to communicate more information about it. A word or two about scales. Obviously we need to include that for very clear reasons in terms of trying to fit large objects on a small bit of paper. And you use a scale like this, which is 1:2, probably half scale. And having said that, we tend to avoid non-technical terms like full scale and half scale. It's a very casual language. However, you technically meant to be calling this 1:1 scale or 1:2 scale. Okay, but we all know what half scale means, what full scale means. Small objects are generally scaled up. So if you're designing a wristwatch or something slightly smaller, you would scale those dimensions up on the drawing board, on the drawing paper. However, if you're designing a bridge or large objects, a wing section, a wind turbine blade, etc., you would scale them down like so. And since everything we do on the detailed drawing has this particular significance, majority of the role is played by the line types. Now, you got to be very, very careful in terms of selecting the lines and what they actually mean on paper. Generally, all the major details are shown, or the hidden, not the hidden, or the visible edges are shown using a thick continuous line, and the thick line will have a weight of 0.6 to 0.7 millimeter. All the auxiliary lines, which are the thin lines, which are non-structural lines, basically, they will be 0.3 millimeter. Now, you don't need to worry too much about these because most of this will be set up within any CAD system. However, sometimes you have to go in and take control and make sure it is complying with this requirement here. Okay. For the continuous thick line is used to show the visible outline and the edge. The continuous thin lines are shown for auxiliary information. So, for example, dimensions, projection, leader lines, hatching, etc. So anything that is not the edge of the object, you will generally use a continuous thin line. Dash line, and you're probably aware of this already, they are used to show the hidden details which are not apparent on the skin of the object. Chain line, which is a dash and a dot, it's a center line, or we also call them construction line in SolidWorks. And chain double dash is a very special line type, and believe me, there are about 15 different line types even, but we hardly have to use those really. Most of the times we get away with using these line kinds, and that's adequate. If you are interested in finding out what the other line types are, you can refer to the British standards to be able to make yourself aware of that. So we have here a chain double dash line, which is used to show the extreme position. So imagine a situation in an assembly drawing where you need to show things that move, an arm that moves, etc. Basically, you can use a chain double dash to convey that emotion. Okay. Now here's an example of how you can use lines to show various details. So the the solid line on the outside marks the edge of the block here, looking at it sideways. And also there is a cylindrical cutout or a circular cutout that goes all the way from front to back. It is shown using a dashed line. So if you're looking at it sideways, you're obviously not going to see the fact that it's a circular cut. It could be a square cut or a rectangular cut looking at it sideways. When you look at it from front, you're going to see a circle with, and since it's a circular detail, you have to always support that with a crosshair like symbol. So these are using center lines. So this is a chain line. So long dash, short dash, or long dash and a dot to be able to mark the center of the circle. Okay, and as you can see, the thin lines are used to dimension the width of that, and there will be a lot more many dimensions around here to be able to provide all the manufacturing information about that particular part. Couple of other information which you probably will have to use a like a call out option also in SolidWorks, and these are called the leader lines, LEADR, leader lines. And this is where you can actually specify, it's literally click, drag, drop, and the text box pops up, and you can specify some details about that particular face if you wanted that to be polished or painted, whichever way, you know, or like this, which we have seen previously. Now, British Standards is very particular about the arrowheads and the arrow kinds we use. They need to be long and slender like these, and they need to be filled in. SolidWorks by default will not produce these arrowheads, so you need to go in and change that. And I'm going to make another video which will show you how you can do that in the end. Okay, arrowheads need to be about 3 to 5 millimeter long, and it's very specific in terms of the dimensions of the arrowheads as well, or the aspect ratio. So a couple of things about dimensioning. It needs to be very clear, because your original intention is to communicate information about the sizing. So it has to be very clear. They should not overlap. They should be nice and centered. It shouldn't be neat and tidy. So, you know, it's all professional practice. There should be enough dimensions on a drawing to be able to manufacture the object without scaling and relying on unfounded deductions. So we tend to give all the numbers, as many as possible, but adequate. We don't overdo it. Dimension should appear once, and we do not double dimension. So those two, that's not a repeat. So those are two different statements, and I'll probably have an example to show what double dimensioning really means. Okay. However, if you dimension a feature and dimension it again, you have experienced this personally, that SolidWorks will not like it and it will throw an error, and that's correct, because there's no point creating work for yourself if it's not needed. And the fact that it says do not double dimension, that means you need to be aware of the overall drawing as well. I mean, you need to be aware of the fact that if you dimension something in one view, probably you are, if you're redimensioning some other view, then that is classed as double dimensioning. Never ever dimension hidden detail. I mean, there is a very strong reason behind this particular statement, because hidden details are not true details. They are concealed within an object. So we try and avoid dimension hidden details completely, and only dimensions shown on assembly drawing are the overall dimensions or the checking dimensions. So never detail dimension the assembly drawing as well. Okay, once again, something we can get carried away with dimensioning, because it's just so easy to get it done in the CAD package. Now I have a few examples here of incorrect dimensioning, and this is obviously going to reinforce the need of the correct dimensioning. Whenever you dimension, we gotta make sure that there is a very small gap between the actual part and the dimensioning detail there. Okay, and this is to make sure that there is no confusion in terms of where does the object stop and where is the dimensioning detail. That's why there is always a small gap to make sure this happens. Also, the fact that the numbers need to be sitting nicely centered. Probably that's slightly higher than what I generally like. However, it kind of gives you a good idea of what dimension look like. I can't really agree with this arrow kind. That is an equilateral triangle, but as you seen in the previous image, we are generally we go with isosceles triangles, so long and pointy arrows. Really, that's what we need. Okay, so it's very clear from this particular example that the numbers are probably too large, because if you think that's the reasonable dimension, then it's probably in here the font size is too large, so that's what's wrong with this one. There's a small gap here which is correct, so that's not a problem at all. Here maybe along with the arrows the font size is too small, so that's an error right there. Here the number is sitting below and it doesn't look very centered to me, so it should be above the arrow and centered as well. That will make a really pretty dimension. Here we have stick arrows, which is clearly frowned upon. It's a non-standard. According to British standard, they need to be filled in, long and slender. Here the projector lines are touching our object, which can lead to confusion, hence this is incorrect. Units, this is not necessarily incorrect in case if you're dealing with a drawing, which is probably if this is the only unit, or if this is the only dimension which is in metric system, then probably that's not wrong, you know. So we can talk about that one. Well, generally standard practices avoid units. If they're all millimeters, just have a little message in the title block that says all dimensions are in millimeters UOS. Once again, we have a non-standard unit system here, and the projectors go unnecessarily past the dimensioning arrow. Here the dimension arrow is not touching the line, so once again it's necessary to be able to explicitly clear in terms of which space we're marking up as 30. Here the gap is too large, non-standard, and here there is no overhang. We've got to have a bit of an overhang, and the arrow needs to be contained within the projector lines. Here we have an example of a situation where we can see double dimensioning and repeat dimensions. Before we go into the detail, let's have a look what we're looking at here. This is basically the same object. We're looking at it from different directions, so maybe front view, and this is the side view. There are two cylinders tacked onto each other. First cylinder is 25 diameter and 25 long, and the second cylinder is 30 diameter and 100 long. Okay, and this is the same object, and if we look at it sideways, this direction, we will see two concentric circles sharing the same center point. The reason this is a case of repeat dimension, because these two views here, the front view and the side view, or right hand side view here, there is a repeat of these dimensions here. So 530 means the diameter, which is the width of this rectangle here, which is given here. That's the same feature, and so is this. That's also the same case. So in this particular case, ideal scenario is to avoid dimensioning these details on the front view, and I prefer to see diameters in this view here like that. That's a bit of a standard. Whilst if you hold the object sideways, what is more apparent is the length. So it's always acceptable to have the lens onto this particular view. Now this is a case of double dimensioning, as I said before, because if you think about these two dimensions, these details here, we got 100 here, signifying the length of the cylinder here, this big cylinder, and we got 25, and up there we also have 125, and I think we can conveniently let go of one of these dimensions. The reason behind that is one of these can be just a checking document. There is no need for us to specify 125 here and 125 up here as well. That causes confusion. Now we can discuss which one of these dimensions you want to let go, which one of these is unnecessary. And from my point of view, I think I would love to keep this 125 and this 100, really, only because I'm relating to the manufacturing of the unit. You know, the gesture of leaving the 125 in this drawing means anybody who is going to manufacture that, they have a really clear idea of what kind of a billet they need, how big the dimension it needs to be. So they know immediately that they need to be working on something that's slightly higher than 125 and thicker than 30 as you can see from this view here. And once you have that dimension, generally the operation would be to turn this diameter down to 25 millimeter here, and making sure that whatever that distance is, that can be a checking dimension as long as we make sure that this is 100 millimeter. Okay, so I would definitely try and get rid of that 25. There is the other aspect of double dimensioning, which actually clashes with tolerancing. So for example, on this technical drawing, there was a note here in this corner that says all dimensions are in millimeter, and the tolerancing is plus minus 1 millimeter. So in that scenario, your this dimension here becomes 99 and 101, that is the acceptable limit, and this becomes 24 and 26, that is also the acceptable limit. However, if you look at the tolerances at here, that becomes 124 and 126, which then that conflicts our higher condition and the lower condition on this end, really. And that's also one of the reasons why we must avoid double dimensioning. It is a bit of an acquired process. It takes some thinking about, and also having some manufacturing knowledge, if not manufacturing knowledge directly, probably anticipating how something can be made, definitely helps pick your dimensions wisely. Okay, only because a CAD package can dimension anything you would like to click on, that doesn't mean we should be dimensioning all the random details. You know, they need to be sensible, and the drawing has to be neat with optimum amount of information also complete. So in this case, definitely let go of this 25 here, that 30 and that 25, to make it into a nicer, more acceptable drawing. There are a few more guidelines in terms of the lettering and numerals that you can follow on a drawing sheet, and these are very, fairly standard. Everything should be in capital letters, and the minimum font size should be 3 millimeter tall, and these are standards according to British standards. Not changing the text direction, it should be more or less the same direction. And underlining is not really recommended, because every detail on the drawing paper is equally important. So underlining is a gesture where we tend to highlight when we mean something, when we want to emphasize something. However, on a technical drawing, the practice of underlining is not suitable. Next up, we're going to talk about projection. Now, what I mean by projection, it's kind of shown here through the drawing. As you can see, there is an artifact here, looks like some kind of a valve or maybe a coupling, that's drawn in 3D, clearly a simulation, because you can see that's made out of clay, gray, and we can see the drawing sheet that's placed on it actually has a projected view of that. So whatever we see on this direction, that's that view there, and that's the front view, the side views, and the top view, etc. So in this section here, we're going to look at different ways of projection. Now, what's also important is understanding the reason why we need to look at projection systems. This is something to do with our intrinsic strengths, which is we find it easy to visualize shapes in 3D, while as printing or drawing a 3D shape directly without the help of a CAD software would be quite complicated, and that's why we tend to use 2D projections of a complicated 3D object, which then by the time you say, I'm not going to worry about all the dimensions, I'm just going to look at the 2 dimensions. And if you were to look at the object from different possible views, you get a bunch of 2D views, which then allow you to put together all the information in 3D. So that's, and also the fact that in technical drawings, we are pretty much restricted to a two-dimensional piece of paper. Paper is not 3D. Paper is definitely, basically a two-dimensional sheet. So anything that's drawn 2D on a 2D sheet makes a lot of sense. There's lots of room for error for creating illusions, creating ambiguity if you were to create 3D drawings on a 2D paper. And also it's a skill that probably we are not everybody is equipped. However, if you were to look at British standards, it kind of breaks down the rules for drawing items in 2D. Okay, so let's take a look at different British system. The first one, and probably this is the absolute one now, it's not very popular anymore, but this is for information only. It is called the first angle precision system. And there is a third angle precision system, which is more popular, and that's also known as the American precision system. You probably in your working career you might end up looking at either of these. Chances are it will always be a third angle system. On the drawing page there will be a symbol which shows you what system was followed to create that particular drawing. So be on a lookout for that symbol. We'll look at that in some detail later on. The way third angle system is set up can be demonstrated with this block diagram here. So when we let's just say we have this cube here, and I'm going to label the sides of the cube as E, B, C, E, A, so A to E. And if I were to indicate my front view, my direction of orientation, basically this is my orientation looking at the box from this side. So this is my front direction. What that really means, according to third angle system, is I can draw the front view right in the middle. That becomes my anchor point, and all the views are organized around it. Now the third angle system, what that really means is the way these views are organized about the front view, and it's fairly straightforward to understand, which is you have the left hand side view drawn. So whatever you see from the left hand side of the box, so if we're going to see view A, I'm going to draw that on the left hand side here. The right hand side view, which is the view C, I'm going to draw that around here, which is on the right relative to the front view here. So it's basically, if you imagine that as being a cardboard box, and on the day of the recycling you're basically unpacking that, and if you expand that out, this is what you're going to see basically. So front view there, top view there on top, very logical. And you may realize a good CAD package will have quite a lot of indication of these icons. So if you're picking a different view, it will be reflected through the icon. So probably that icon will be above the front view to be able to see the top view, etc. Okay, so keep an eye out for a system like this. Once again, to summarize, third angle system is all about the way we organize our views, our orthographic views on the drawing sheet, where we will have the front view sitting right in the middle and all the views are organized around it. You will have bottom view below that and top view above that, left on the left and right on the right, and the back view on the right hand side of the right hand side. So that's something that's very peculiar about the third angle system. It's probably going to be easy for us to understand if we look at an object. So here we have an automobile which is sitting in a glass box, and let's pretend the user or the viewer actually moves around. So if you were to say this is my front direction, if you were to move on the left hand side, what you see on the left hand side will be your left hand side view, and if you were to move up and look down on the car, you will see this drawing here. So and that's going to be your top view because you're looking top down on it. Let's have a detailed look at the line work in the projection system. Once again, we have these two blocks. They are stacked right next to each other, and what we have here is a very simple 3D object, really not difficult to visualize anyway. However, if you look at the 2D version of that 3D object, it's even simpler. So whatever we see from this direction here, this is a front view, front direction. Okay, so imagine if you're shining a torch at it and you're traveling through light. When you shine the torch, probably the first face you're going to hit is going to be this face here, and the light is traveling really slow. So you're going to see that, right? So what I tend to do is draw that as the first detail in solid visible line, basically continuous thick line for the visible edge. Okay, and the light travels further, and then the next, you're not going to see this slightly darker blue shade because that's along the line of sight, and you're going to completely miss that because that's, you can't see that, that's along there hidden behind that edge really. and then you're going to see this bit here, which is that bit of rectangle which is shown here, and that completes your front view. And if you look at the same object on the right hand side view, you're gonna, once again, if you shine the torch at this, you're gonna see this darker shade of blue, and as you travel further you're not gonna see these two faces because they're along the line of sight. However, you're gonna see this this space here, which is then shown as that. And also exactly same logic applies when you're looking at it from the rear end, where the detail which doesn't really belong on that side, however the detail is there, you got to acknowledge that with a hidden detail which is drawn using a continuous, no, it's not continuous, it's a dashed thin line. Also easily available in a good CAD package. As I probably have said before, these views remain connected to each other. So whenever you produce orthographic drawing on a piece of paper, either manually or using a CAD system, you should expect to have a connection between those. So for example, these lines will remain collinear, and the relationship between that and that is at 90 degrees. So everything is 90 degrees around here as well. I was referring to this particular symbol here, so expect to see this symbol here every time there is a third angle project system. This is what you're also expected to provide every time you produce a technical drawing, just to be able to educate the reader which projection system you're using. Now if you think about it, the third angle icon here is actually a drawing produced in the third angle system, which I find it quite easy to understand and remember for future references. You know, I tend not to think about first angle system as it is, but I know if I'm looking at a cone here without well, basically it's a slice of cone, I would see two concentric circle like this if I'm looking at it from the left hand side. So that kind of, to me, that stands out as a drawing produced in a third angle system, hence I remember that as the icon of that. Okay, so something you need to be looking out for, also something you need to be actively creating and producing on your drawings when you are the designer. Okay, there are a few details for you to bear in mind. However, a good CAD system will produce these for you automatically, taking into account all the details. A couple of words about circular features. You should expect to see dashed lines whenever we have a detail that's not apparent. So this geometry here, which is a box with a couple of cylinders, one on the side, one on the top here, and if this is your front direction of viewing, that's the view right there. Okay, and what's peculiar about that is the fact that we are expected to draw a center line. So every time there is a circular feature, we got to draw a center line there. Let's pretend that you haven't seen that. You don't really know what that object looks like. But if I were to produce these three views, that should be enough information for anybody to understand what that is, obviously along with the dimensions. So if I see a rectangle here with a center line running through it, I know it's not a rectangle, it's a cylinder. Same story applies here. We got a cylinder, and very clearly we are looking at a circle straight on, so we are expected to draw a crosshair like pattern where we indicate both the axis like so, and all of these lines tally up. So something you need to bear in mind to be able to produce meaningful technical drawing. You always have to imagine that you want to produce and provide information with probably only two views, and that should be enough for anybody to deduce the object they're looking at, really. And if you were to think about that and that view together, or maybe that and that view together, that's kind of enough to know what this object is. Once you kind of seen it, it makes it easy as anyway. It's difficult to unsee that. However, if I hadn't seen that, I kind of know there's a center line there, so that's a circular object. There's a center line there, that means that sits centrally, etc. So there's a lot of information that's going that we can tally. Now we got a couple of exercises here where we can look at the 3D object, and we can look at the orthographic projection of that, which is drawn here. Now whenever we have technical drawing, you should expect to see 2 to 3 views, although in previous examples I've shown you more than 2 views, more than 3 views here, but that's not a common practice. It's generally a standard to produce 2 to 3 views only, and that is enough to convey all the information about the 3D geometry, right? So let's just look at this geometry here, which looks like probably a couple of steps leading into the door. What would you see? And in all of these examples, positive y direction is your front view here, okay? So the minute I know the front view, I'm going to plot that into the onto the junction. So right now I'm going to start with the front view right there, and as I go in, I'm going to see that face there, which is drawn there, and as I go further in, I'm going to see that face there, which is drawn right there on top of that. Really, we're not going to see these sides because they are along the line of sight, so we're going to completely miss them. If I look at this object from right hand side here, I'm going to see that sideways L pattern. I'm not going to see any of those faces which are along the line of sight. I'm going to miss that completely. And that view is drawn on the right hand side of the front view. The top view exactly the same. We're looking down at it, and we're going to see that grayed out portion and that grayed out portion indicating 2 rectangles stacked above and below. Somewhat similar goes on with all of these examples, and you're more than welcome to pause this video and just look through these drawings and make sure everything tallies up. Something which can be peculiar, and if you're new to technical drawings, probably there might be views that you think, oh, no, this doesn't make any sense. You might think this is an illusion, or this is, well, it isn't. Most of the times all the lines on the screen will have a certain meaning, will have a deeper meaning. So sometimes you just need to try and take it all in bit by bit, really. So for example, an object like this, which is actually quite not something we see every day. However, once you look at it, you think, okay, that's quite possible. We can model that quite easily. When producing the technical drawing for that model here, you need to bear in mind that the details which are not apparent on the skin, so positive y direction, looking at the front view here, there is this cutout done, which can only be represented with that dashed line there marking the depth of that cut right there. And if you look at the same object on the right hand side, the notch here, that will leave a horizontal dashed line marking the depth of that cut. And if you look at it from top, all the details are apparent and there are no hidden details. So they can actually be quite complicated at times to look at. However, it's, as I said before, it's probably, you acquire the skill by looking at these drawings over and over. Sometimes it's probably a good idea to just look at this and then not worry about that, and sit down and try and draw that, freehand if you think. It's probably good practice, something you need to be careful about the circular features, and whenever there is a cutout, you should expect to see these 3 lines, okay? The outer 2 lines indicate the waistline of the cylinder, and the middle line indicates the center line, or the location of the center point of that cutout. And there is a rhythm going on through these drawings like so, okay? This one is a very peculiar one indeed, because there is a tangential relationship between this cylinder here and this bit of detail here, so it wraps around quite nicely in a smooth manner, and that actually results into a lack of edge here. So when we look at this, without seeing that, it can be quite confusing. However, there are a couple of other views here which kind of gives us information about what might be going on in that region, and looking at that, I know that wraps around that, hence there is no edge. Edge is only formed when 2 surfaces intersect. Here there is no intersection. This is a smooth transition. If you were to run your finger on it, you try and run your nail on it, you will not feel the step, because this is a smooth blend, and hence there is no edge. Whenever there is an intersection of plane, that's only when you will have an edge forming, and not in this particular case. So I feel they are really, really interesting to look at, just to be able to acquire that. And once you make that step mentally, you can't go back. This will then stay with you to be able to look at 3D objects in an orthographic fashion and simplify information. And in the final section today, we're going to talk about the most important skill in in every technical drawing, which is to be able to demonstrate the hidden detail. Most of the times we tend to use dash line like so to signify anything that's not apparent on the surface. So there is a cylinder right here, a cutout going all the way through, and we generally use a dash line to show, well, that's what's happening there at that point. Okay. However, there can be instances where that is not possible, and one of the bylaws is to try and avoid dimensioning the hidden details. So let's have a detailed look at when sectioning might be appropriate. Think of a spindle here, which is stepped on the outside, and it is also stepped on the inside. Now, one of the regulation within the British Standards 8888 is to not dimension the hidden details. So this phi 17 here is actually incorrect, and that is not allowed as per the British Standards. What is allowed though is to be able to tilt that object sideways and probably refer to some other views, and when that becomes a visible edge like this in this particular scenario, this is what is an acceptable practice. So sometimes you can pick an appropriate view to be able to communicate all the details on the inside, and this is actually quite a nice example because all the circles are quite nice and they go in one direction only, so you are able to see all the diameters and all the heights in either this view or in this view, and that kind of complements each other, and this is probably the better practice. But when it's not possible, we generally go through a system that's called sectioning. And sectioning really means that we pretend we are cutting through an object to be able to reveal the inside details. And if you can imagine literally cutting a bit of wood which leaves the saw mark behind, and we tend to use a technique called hatching to indicate that something has been chopped, and we are revealing the insides of it so that we can dimension that fully, and also we can then educate the reader about the details that sit within the object, which is more or less every single time when you are working on a part drawing. You will hardly have anything which doesn't have any details which are concealed within an object. So this is definitely in 95% of the technical drawing you'll see will have a sectional view going through it to reveal the insides. Okay, so once again, what we assume here is this particular part here, which is it's not possible to dimension this fully without opening it up, and we just pretend that we are going to cut it out. So we create a cutting plane there, and then we show the insides of that like so. So we can say this is the front sectional view or sectional front view, etc. And this then allows us to dimension these diameters here, these heights, and this diameter here without breaking any rules. Okay, something which can trip you basically. So there is not much difference in these two terms here, section view and sectional views. However, the correct term is a sectional view. Section view is you're taking a really small, a thin, infinitely small section at that cutting plane and representing that on a piece of paper. That's called section view. Section view. We do not generally use this particular mechanism. However, the one which is common in engineering is producing a sectional view, one with AL, which actually shows the material that's been exposed and the remainder of the part that's hiding behind it. That is included. So it's basically, this is half the part in this particular case, and as you can see, the insides were revealed to show the different steps. So we can now safely go in, diameters in here, and all the lengths without breaking any of the rules. And this is probably just as important, to be able to identify your cutting plane. On the drawing, on the technical drawing, you would generally show this kind of a line pattern, which looks very similar to a construction line from SolidWorks. However, it will have some peculiar turning points and the stopping point when produced, and this is called a cutting plane. This indicates the point where you are assuming the part has been cut open, and then you are allowed to reveal the details of the part on the inside. One example you can see is this coupling here, where you probably have those two flanges, a bit of pipe section in the middle, nice bit of fillets blend it all in quite beautifully. And there is a little notch here, probably just to, to be able to locate, to be able to stick a wrench on it, and then make sure that you twist it and you organize that into the right place, apply a bit of torque to it really. So that is the detail right there. Now, how do we use the sectional view and the cutting plane? Like so, that's shown here. So we have this front view looking at the coupling from front, and this is the side view here. All of a sudden, since we have a cutting plane right here cutting through that point, what we are going to assume is we are going to discard that. These arrows actually give you an indication of what is it we are removing. So if you can imagine this as a literally cut extrude command from SolidWorks, where we cut away stuff that we don't need. So we are deleting everything in that direction, and we are retaining this part here. This particular view is actually what is left now. So we're going to reveal the inner diameter on the outer diameter, and also that notch is going to be apparent right there, and some mounting holes. I must admit there should have been some hidden details here to indicate these mounting holes onto the right bed. Also, try not to forget to label the drawing as sectional view at AA, indicating, because you may have more than one cutting plane on a given drawing. Also follow that with a with the projection system symbol. Now, hatching can be quite complicated at times, where you have multiple parts coming together, and you want to show the insides of it, and there are a few rules and regulations you may want to follow regarding hatching rule, and British Standard is actually quite descriptive in this particular field. So when we have a normal pipe section, this is just a case study really, and this kind of gets more and more complicated as we go through this. What we have is a hatching pattern indicating the extent of inner diameter and outer diameter. So that's my inner diameter there, and that's not being hatched because we are not going to cut through it, and that is actually a curved surface which is behind it. Okay, and how do I know this is a pipe section and not just a rectangular box? Because there is a center line running through it. That means this is a circular feature. Okay, I know that now. So the hatching direction is maintained there, and that indicates it is the same material at that level. So we don't need to change the direction, etc. However, when we have more than one part, as you can see clearly from here, there's a collar that fits onto that pipe there, and I want to indicate that by changing the hatching direction. So one goes 45 degrees and other goes minus 45 degrees, just to indicate that bit of a difference in material. And that's actually quite nice to be able to see there's a distinction between those two parts there, as you're cutting through more than one part at that level. Things get quite complicated when we have more than two now, and in this particular scenario, you're allowed to change the spacing between the hatching lines, indicating there is a change of material. One of the other rules around sectioning is, in fact, it is designed to make it quite simple and quite straightforward, and to avoid creating extra work from the designer point of view and from the reader point of view as well. This is when there are some regulations around the standard shapes, and this, one of these is basically a spindle. So whenever you have a cylindrical spindle object, we are not going to hatch through that. We are not even going to section through that really. So that's something you want to remember. And there are some more standard shapes where the sectioning rules are quite peculiar. So for instance, this spoke here, there is nothing to show on the inside of the spoke. These are the standard, filled material. There's no need to hatch those, and that's why this is not a good practice right here. However, around here we can see everything else. So this time our cutting plane is not a straight line. It is actually a revolved view here, where we have part of the cutting plane is looking this way and the other part is looking that way, because there is no way carrying on with this line straight in this direction. There is not much to demonstrate. However, there is a key way this way, and hence the designer in this case decided to go from there and then change the direction. That is allowed. That is a perfectly good practice there. The way we produce this is, if you are looking at this object from the left hand side here, whatever we see below that level, we draw that there, and then the rest of the view is basically that is rotated above there, and we draw that as if that is literally stretched out up to this point, which is accompanied by the label that says sectional view at BB. Once again, try and avoid sectioning standard parts. If there is nothing to show on the inside, a very common scenario is web or a rib, where it's basically just a bit of material to be able to stop and apply, stop the collapse of these two features and apply some stiffness without adding loads of material. There is no need to section through that, and this is what you would do if you happen to cut through at that level. We are going to cut through the rest of the part. However, we're going to draw the webs as standard, and the rest of the part will be exposed to show the insides of it. Things will get a bit tricky whenever we have threaded shafts and threaded holes, and there are a few things you probably want to bear in mind whenever there is a situation like so. Okay, the threads generally are they're dependent on what thread type you're following. They can be anywhere from a trapezoidal form to a triangular to probably a square, which is not as popular. Now in the UK we generally follow a metric system where something like M8 actually means a nominal diameter of 8 millimeter, and M stands for the metric, and there is only one thread type. So if you were to go to any of the DIY stores, you'll be able to quite easily buy the fasteners if you were to follow this regulation here, okay, this guideline here. There are a few things that you need to be bearing in mind in terms of sectioning through a threaded shaft or a threaded hole, and the illustrations are provided here. Once again, the threads are not literally drawn onto the drawing paper. We generally use a thin continuous line to indicate the part of the hole. So this is actually a female body, and the female threads are represented on here. Really, every time we create a technical drawing representing that, we will always have a 120-degree angle inflicted by the drill at the end of this, really. So we tend to, if you can imagine, this is a solid angle, 120, quite conical shape around there, and the rest of it is cylindrical. However, we are also needed to accompany that with a double line indicating the waistline of our threaded hole here. This is a blind hole, and I'm sure you are aware of the terms blind and through, and those are exactly the same around here. Okay, blind is a very definitive depth, so the hole goes up to this point only, while in through hole it goes all the way through from this surface to the other, and also there is a double line indicating the presence of threads. Something very similar in terms of sectioning the shafts through the hole. You have to bear in mind that standard components like a cylindrical shaft, once again, they fall in the category of a spindle. They do not need to be hashed in. However, the rest of the material around it can be hashed in. Once again, the shafts are can be threaded, and we need to indicate the threads, a presence of threads on the shaft by a continuous thin line, as you can see in this particular drawing. There are a couple of different kinds of sectional views you may come across, and that there are more than what these slides cover. So there are broken out sectional views as well, so it's something you need to be aware of, where we choose to just pick a small section and just zoom that in and demonstrate the details within that small section. That's called a broken out section view. Here, this particular view is called a staggered sectional view, where we have a staggering cutting plane, and then we tend to then draw the details. If there is no point restricting yourself to draw only a straight line as your cutting plane, because then if you did that, you miss out on these details. You don't get to show these details. However, it'll be quite convenient to be able to imagine this as actually a literal cutting operation, where you are allowed to maybe laser cut this. So you got the laser, which moves like so, literally removes this material, and what you're left with there is produced around here. Now obviously the inclined lines indicate the hatching, which mean the material was removed around there, showing the saw marks. Another sectional type is rotated sectional view, where once again it probably wasn't possible to create the sectional view using one straight cutting plane. So in this particular case, the designer has gone across at the pivot point and they've gone down like so. And in this particular case, you tend to draw your sectional view looking at it straight on, and then you add this bit of sectional view to the drawing, really. So if you can imagine, there's a division here, and that is that bit there. Everything on this side is what you see around here, and from point C this way is what you see along here, along with some uncut material which is right there, which is shown here. Okay, so I think that is quite interesting. Following on that, I have some examples to show you, which will probably reinforce what we learned so far. We have, and this is what a technical drawing will look like on a regular basis now. Okay, it's not going to be just about the orthographic views. You will definitely have to consider making one of these views a sectional view. So in this particular case, the front view is the sectional view, and also the front view, really. So this is the front sectional view, or the sectional front view, and this is what you should expect to produce as well. So a 3D object like this, where you have a couple of cylindrical cutouts and a step down as well, where that's the platform right there. If you look at it from top, this is what you're going to see. However, it's quite complicated to be able to show all the details on the inside, so the designer has decided to apply a cutting plane right in the middle, indicated by letters AA, and the view is produced around here, which is accompanied by hatching. We have the same object, looking at it from the right hand side, and this is the view we are going to see. Obviously it will take some time for you to look at it and make sure all the details tally up, and all the hidden details are all catered for. And there are quite a few of these examples where you can look at it and you can walk through these to be able to understand the act of sectioning and producing a sectional view. In this particular case, we are looking at just a partial sectional view here, where the cutting plane went only about that much, and we have removed that quadrant there, and we are revealing the details of what remains behind. Something similar here. We are removing a quadrant there to show the inside of that particular part. Finally, we have a staggered sectional view here to be able to contain all the details of this cylinder here, and also the designer decided to then step down and then also take that on in the same view. And as you can probably say, the front view is basically a representation of this, judging by the cutting plane and direction. And there would be a side view here, which is, I don't think that's shown in this particular view, but the side view will be whatever you see from that side after you remove items on the right hand side of the cutting plane. Now that's the end of that session. If you have any questions, let me know. You can comment on this video as well, and I'll be able to reply back to that. Have fun.